Good morning to all of you. I am Devendra Kumar Patel from VIT Vellore, India. I welcome you all in the session of hands-on computational fluid dynamics. Here we are going to set up the boundary condition for the present problem, and we are going to post-process it using ParaView and take plot. This is the second video of the present session. In the first video we have generated the mesh inside the computational domain. Our computational domain, I want to show you, it is actually an impinging jet as shown in this figure. A slot impinging jet we have considered for the simulation, where the nozzle exit provides a jet of velocity v0 which is impinging onto a stationary flat surface. This nozzle is a kind of slot nozzle, and here we are having left, top, right, front and back. These boundaries are open to atmosphere. I will first show you the mesh which we have generated in the previous lecture. I am going to plot the mesh which we have generated using snappyHexMesh and then extruded to get the three-dimensional mesh. So here a three-dimensional mesh we have made as it is shown, but the mesh which we have made is very coarse mesh, and that was to show the procedure how to make the mesh. But the requirement for the simulation of impinging jet turbulent flow using large-eddy simulation with volume model, the requirement of mesh is very dense mesh. So we have already made the dense mesh and simulated the case using OpenFOAM. We are not going to use this coarse mesh which will not give the accurate results. The information of this mesh, like number of faces, vertices, coordinates of faces, vertices, all is inside this polymesh, which is inside this constant directory. Inside this polymesh you can see there are cell zone, phase zone, faces, neighbor, owner, point zone. So this is all the data of meshes which is generated by snappyHexMesh. The most important file is this boundary, where we can see the different boundary where we can provide the boundary conditions are named as front, back, inlet, outlet, left, right. So actually if they are saying right face, that means these are the faces are considered as right face in the mesh. Okay, in the same way, if they are saying, we are saying the front, so there are 8646 surfaces are considered as front. So they are having the information. At this point, if we want to change the name of any boundary condition, like if I want to change inlet as the nozzle exit, I can change here, and onward I will use, instead of inlet I will use nozzle exit. So whatever is comfortable for us, in the same way we will keep the name of the boundary condition here. And after changing this, we have to copy this all data which is having the information of mesh, and we'll copy this data wherever we are going to set up the boundary conditions for the simulation. So we are going to simulate the large eddy simulation So I have already copied this polymesh directory to another directory which is named as LES. So I have copied those data inside this polymesh. I have pasted the polymesh data here, but as I have told you, we need a very dense mesh, but whatever we have generated in the previous session, that was a coarse mesh. So I am going to use a dense mesh here, which will not look exactly same what I have shown in the last session. As per my requirement, I have renamed the boundary conditions and I have given some more information, like I need the front face which will be kind of open to atmosphere, but as we have considered it is a slot jet, that means a very long nozzle is there which is providing a slot jet to the flat plate. So I need a cyclic kind of boundary condition for the front and back. That's why we have just written this small code here. In the same way, you can see for the back also we have provided the same kind of code, and we are actually we are going to provide cyclic boundary condition for the front and the back surfaces. That's why we are mentioning here. And then we are having a plate. Okay, so plate I have written here. I am writing left B, that means left boundary of the three-dimensional computational domain, and I am writing pipe. Instead of writing nozzle, I am writing pipe. And here top is the top surface which is again open to atmosphere, and we can provide any kind of boundary condition. That's why we are writing patch here. Okay, the pipe is wall, so we have to be careful, it should be wall only. And these are the number of faces, and it is starting from which number? It comes from the snappyHexMesh, so we are not going to change these things. We have to just check wherever we want to put any boundary condition, that should be named as patch, and wherever is the wall, we have to explicitly write the wall. Okay, and the cyclic boundary condition we have to provide for the front and back, so we are writing here cyclic. After doing this, we have to see the boundary conditions. Okay, we are going to put the boundary condition. Before boundary condition, I like to show you the different surfaces which we are having from this mesh. So for that we are going to use ParaView, and we load this mesh into the ParaView. So we will open the ParaView here in the same directory like this. I am going to load the data, that is our polymesh directory, whatever mesh we are having, that we are going to load. So these are the surfaces loaded by our ParaView. Now we can check one more thing, what are the different surfaces we are having here. So presently we are showing the internal mesh. So here in this domain we are having the mesh. You can see the mesh by clicking here. This is the mesh. Okay, so it is very dense mesh. It is not like the mesh which we have made in the previous session. Now I want to just see where is my nozzle. As we remember, we have given the name pipe. Okay, and inlet is the nozzle exit. So now we'll able to see this is our nozzle. Okay, nozzle surface. This is our nozzle surface, and it is meshed nicely. Okay, this is the exit of the nozzle. We are not having any surface on the front and back because it is a kind of slot jet and there is no surface here. Now we'll see the right. Okay, the right surface, you can see the right surface is here, okay, which will be considered as right boundary, that is open to atmosphere. In the same way, we are having left boundary, you can see this is the left boundary and this is the top boundary. Okay, we are having back like this, the back surface, okay, and in a similar way we are having front also. So it is here, the front surface like this, and we are having plate. So plate is the bottom surface which will come here at this location. We can see it nicely using this surfaces and edges. So our plate will come here. This is the plate, okay, this is the plate which we have made. Now the next thing is that we have to put the boundary conditions. So how we are going to give the boundary conditions in large-eddy simulation? So the zero directory will keep all the boundary condition that will be considered as initial condition, and as the calculation will go on, there will be another directory like directory 1, 2, 3, 4 as the time will go on. This is the zero. Zero means initial condition, boundary condition. So in LES we need a boundary condition for velocity, for pressure, new SGS, because we are going to use Wale model, so new SGS is required, and the turbulent kinetic energy. So first we'll see how we have provided the velocity. Okay, so one more thing, when I'm going to provide the velocity, I have to give the velocity information for each and all surfaces which is in our mesh information. Like inlet, there is one surface inlet, for that we have to give the boundary condition and we have to write the values of velocity. In the same way, for the top, for the left boundary, for the right boundary, okay, and for plate and pipe and front and back. So as we have said, the front and back I am considering as cyclic boundary, so that's why we are writing cyclic boundary condition, type is cyclic. So plate and pipe both are wall, so that's why we are writing type fixed value, and we are giving the value of velocity, that is 0, 0, 0, because plate and nozzle both are not moving, so it is not having any velocity, so we are giving 0, 0, 0. That means three coordinates, the x component of velocity, y component of velocity, and z component of velocity. Here in the left boundary, in the right boundary, which kind of boundary condition we have given? The pressure directed inlet outlet velocity. So actually there are different kind of boundary condition available in our OpenFOAM, and here we are considering pressure directed inlet outlet velocity. As I have said, the left, right, front, the top, these all is open to atmosphere. So in this location pressure will be constant, will be equal to atmospheric pressure, but the velocity will be directed by the pressure. So here a special kind of boundary condition we have provided, that is pressure directed inlet outlet velocity. If we need the further information about this pressure directed inlet outlet velocity, we can directly come to the Google, and it will take you to the OpenFOAM site directly, and there the information about the pressure directed inlet outlet velocity we will get. So here I want to show you that, let it open here. So just I am searching that pressure inlet outlet velocity. There are many more, So this is user guide, and here we can get the pressure, directed inlet outlet velocity. The information about that we'll get here. So what it do and how it works, the all information you are going to get from the user manual. Here one more thing I want to show you, like inlet I am considering. Inlet is actually the turbulent turbulent flow, okay, which is coming out from the nozzle exit. That I am considering as inlet. So turbulent inlet we have given, and we are giving the value of velocity because we are having the inclined nozzle that is inclined at 70 degree. So we are giving the x and y component, so that the velocity when it will come out from the nozzle, it will have the same it will have a exactly perpendicular, the velocity will come out exactly perpendicular to the nozzle exit. That's why we are giving two component in x and y. And here actually we are calling the V inlet and V outlet. This dollar sign is what I am giving the value of this V inlet somewhere else, okay, and I am calling that value here. So velocity we have provided, and fluctuation scale we have provided. So the detailed explanation about this turbulent inlet, fixed value, pressure, directed inlet outlet velocity, this we will discuss later. For time being, we should know there is a one file named as capital U, where we have to define what are the velocity related boundary condition for each surfaces. In the same way, we are having a pressure directory, pressure file, and there also we have to provide how the pressure will be treated at different boundaries of the computational domain. So here all the boundaries we have called, and we are treating in a different way. Like the nozzle exit, that is known as inlet, here we are considering as inlet, we are considering as zero gradient, pressure zero gradient. Plate we are considering as pressure zero gradient. The wall of the nozzle, which is a pipe, also zero gradient. Here the left and right boundary, there we are considering a constant value of pressure, which is mentioned here. Front and back, as it is a cyclic boundary condition, so there is no need to give the pressure values or any other conditions. So the next is the turbulent kinetic energy. In the turbulent kinetic energy, we are providing the fixed value, that is 2 into 10 to the power 5, okay. For right and left boundary, some inlet outlet boundary condition, which is a kind of zero gradient boundary condition. Top is a fixed value, pipe and plate close to the wall, the turbulent kinetic energy is 0, and front and back cyclic. Here I forget to mention you one thing, like when I am going to give any value, it will be given as dimensional value. So here the dimensions like MLT, so it is L square and T to the power minus 2. So meter square per second square. Actually the unit of that is meter square per second square. So in that unit we are going to provide the value. Similarly, here also for the case of pressure, meter square per second square. In the same way, here velocity, that is meter per second, and the viscosity, SGS viscosity, meter square per second. So we have provided the boundary condition like this. Nu T SGS is the viscosity term. It is not like the viscosity, normal viscosity. It is the viscosity it comes in the modeling of SGS. So that's why we say the SGS viscosity is Smagran-Sky modeling. When it comes, it provides a viscosity term that is not like our normal viscosity, but units are same. Further, we'll see the other directories. So in other directories, we have already seen the polymesh, which is having the information of mesh, which we have created using a snappyHexMesh. And in this constant directory, we can see there are 3 more files. So here the turbulent property, in the turbulent property, just we are mentioning, as we are going to use the LES model, so simulation type will be LES model. In the transport property, we have to provide the values of viscosity. Now this is the viscosity, which is the viscosity, like here we are showing the viscosity 1 into 10 to the power 5. If I am using air, then I will write the viscosity of that, and here is the dimension meter square per second. If I am using water, then I will use the water viscosity. It is a kinematic viscosity, mu divided by rho. And LES property, as we are going to use volume model, one equation eddy model, so about that we have to write these things, which is easily available in the OpenFOAM tutorial. Further, the next directory is the system directory, where we are having the 3 main files, that is FV solution, FV scheme, and control directory. First we'll see the schemes. Okay, so inside the scheme directory there are different scheme we are mentioning here, like we are having convective term in our governing equation, diffusive term in our governing equation, transient term. So the different term, how we are going to discretize, that can be mentioned here. Like here they are writing ddt ddt schemes, so it is related to d divided by dt, so that is related to the transient term. I am going to discretize the transient term using backward scheme. Okay, the gradient term, I am going to use the Gauss linear. Gauss means this is actually second order central difference scheme. Okay, they are mentioning as Gauss linear. The information of different schemes are also available in the OpenFOAM user manual. So from there we can choose the required discretization scheme. There are different schemes available in OpenFOAM, so we are using to discretize the divergence term in the governing equation. For that u we are discretizing using Gauss limited linear. And the Laplacian schemes, so it is for what? Actually, if the mesh is having non-orthogonality, then the corrected scheme is required. If the mesh will have exactly orthogonal, then there is no correction in the velocity is required. So based on the mesh quality, the corrected scheme, and without correction we can use. In the next directory, that is FU solution, how we are going to solve, and we are going to iterate the different algebraic equation. Like for pressure, I am going to use GMAX solver. It is a fastest iterative procedure. Different procedures are available, like Gauss Seidel iteration, LU decomposition, and conjugate gradient method. So GMAG is also one kind of solver which solve the set of algebraic equation and we are using that to solve the pressure equations. Now here here what we define, the different values are there, and one by one we'll look in these values later. For time being we are just skipping it. In the same way, in the FV solution, how we are going to discretize, how we are going to solve the algebraic set of equation of u, velocity, and k, so that we are using Gauss-Seidel iteration method, and we are going to use pimple scheme. So it is here they have mentioned like an outer corrector, that means it is going to correct the velocity, the velocity the velocity 2 times, okay. And non-orthogonal corrector is 1, that means if we are having non-orthogonal meshes, then we have to put the value 1 at least once in a loop. It will correct the velocity component as per the non-orthogonal faces of the mesh. Further, we'll see the last control directory. It is the very important directory because we have to mention the name of application. Like here I am using the PimpleFoam. This is one application in which we are having different solver like large-eddy simulation, different RANS approach. So we can call those turbulent solvers, turbulent flow solvers, through this PimpleFoam application. There are different applications available in the OpenFOAM. Here the start time, end time, stop at, end time. So this is the different values which we have to provide to run the simulation. Like start time is the latest time. That means the latest time of our directory is what? The latest time is 0. Okay, this is the initial condition we have mentioned, so this will be considered as latest time, and from there the iterations will start through pimple scheme, and it will simulate the incompressible turbulent flow. It will end, the solution will be stopped at 0.4. At this time it will stop. It is in seconds actually, because we have given all the boundary conditions in dimensional form, so the time here will be considered in seconds only. So what is the time step? The time step, we have given a very small time step, but one thing we have to note down here, the adjustable time step technique is there. So as per the flow velocity and the size of grid, if this will give a large values of current number, then automatically the time step will be controlled. So we are keeping the maximum current number 0.5. so wherever in the domain, if the current number is increasing more than 0.5, then the time step will be automatically reduced to lower value. So throughout the simulation, the adjustable time step is going to control the time steps based on the current number, so that the current number will be always lesser than 0.5 throughout the domain. Okay, there are few more information that we want to collect, that's why we have written this code, right? So here we want to collect with the simulation, the velocity values will be averaged with the simulation. As the simulation will go on, the velocity will be averaged over the time. With that, it is going to calculate the prime values of different velocity components, and then here the pressure, average of pressure will be calculated, because we are writing on average of new SGS viscosity, that will be calculated, and average of turbulent kinetic energy will be calculated. Okay, there are many more post-processing thing is there, but for time being, how how we are setting up, I have told you. I want to show you again the size of mesh which we have considered in this simulation. So just I am clicking here and showing the property. So it is 328 MB. It is too dense mesh. So it is not possible to run this program, and we cannot make videos also for that, because each iteration will take a long time in one core if we are running. So the multiprocessing is required for this kind of simulation, and we have used multiprocessing and processed it, and we got the solution, and directly I am showing the solution which we got. So here I have pasted the solution which we got after 0.4 second, because we have simulated this problem in a workstation which was having 40 number of cores, and this simulation has taken around 25 days to simulate. So after that we got this data, and directly I pasted this data here to show you the results only, and how we are going to do the post processing. So here inside this data you can see there are many files, different many files. We have started with what? We have started with only these 4 values, like U, all component of velocity, pressure, T, SGS, viscosity, and turbulent kinetic energy. But after the solution we got so many files. It is not like that. This is only the primary variables, U, pressure, and and another is what? SGS, viscosity. This is our primary variable, and K is the primary variable. Other variable we got after post processing. That means if I want to know what will be the values of curl, why we find out curl? To know what is the omega x component, omega y component, omega z component. So what we'll do, we'll find out the curl of velocity, and each component of that curl will provide you omega x, omega y, and omega z. So curl operation we have done, and after the curl operation you can see curl of velocity we got. Then we got the components of that velocity. Then we got the components, like now curl ux is actually representing the omega x component, curl uy is showing the omega y component of the vorticity. In the same way, like we got curl uz after post processing. We got the components of ux, uy, uz, that is the components of velocity in x, y, and z direction. And here the mean velocity we are calculating with the simulation. So the values of mean velocity you will get after the simulation. In the same way you are going to get the mean velocity of turbulent kinetic energy. The mean velocity of pressure you are going to get, because we are calculating with the simulation. The mean velocity of SGS, viscosity, also we are going to get. And all other files which is shown here, it is we got after the post processing of the data. For that also we have made a script file which will work through in OpenFOAM environment and calculates the required variable. Just for example, I want to show you the calculation of turbulent production. Using that same data, a paper has been published in Physics of Fluid. Here I want to show you the turbulent production term. The turbulent production term as shown in figure 9, when we'll expand it, we are going to get the different values, okay, which is required to calculate. For example, this is one component of turbulent production, this is another component of turbulent production. We have expanded the turbulent production and we got the different components, and for at the last we have added all these to represent the turbulent production. So the values, how we are going to find out u prime over bar multiplied by dou v bar divided by dou y, and how we are going to find out this all, we have written a script for that. In this paper we can see we have done different calculations, like here we have plotted the isosurface of verticity, okay, omega x omega y, that we have plotted isosurface of verticity. And we have also plotted the isosurfaces of vertex core using lambda 2, okay, using lambda 2, and q function also. We have used q function and lambda 2 both, okay. So q function, how we give the value of q function, it is mentioned in this paper, and that we have calculated in the flow field. I want to show you that expression. This is the expression of q function. Q is equal to 1 by 2 omega ij minus sij. Omega ij means this is the quantity, and sij, this is the quantity. We have substituted these values here and we have expanded this completely, and we got many terms, differential term, and those differential term we have computed through the script, okay, which is written for OpenFOAM. We have written ourselves, and that script is, I think, with me. I will show you that script, how we are writing that script, and then we have computed this q function, lambda 2, turbulent production, turbulent dissipation, like this many more quantities we have calculated. So after running that script, I want to show you that script. The script is here, that is post pro sh. This is written by us. So here we are using the foam calculator ex, one utility which is a kind of calculator which we use in OpenFOAM, and we will able to calculate many differential expressions. For example, here we are giving one command, components of u, okay, latest time. So latest time is the recent folder. Actually, when the computation will go on, different folder will be created in the working directory, right, like 0, 0.4 as we are having. So we are writing latest time, so that this computation, the command will run in 0.4 directory, not in the 0 directory. This command will provide you the components of u, that is in x, y and z direction, component of ux, uy, uz, like this we can say, components of u mean, components of u prime. So when we'll run this, we are going to get the components in x, y and z direction. In the same way, when we are writing grad of u mean, it is going to provide you the gradient of each velocity component. So like this, there are many expressions which we have calculated through this script which we have written, and after running this script, we got the different properties, important properties in the computational, in the flow field, and that we have plotted using ParaView and OpenFOAM, ParaView and TechPlot. Sorry. Here I like to show you the plot of one quantity. So here I have plotted two lines to show you the comparison. Like here we can see the first line. The first line is at 0.02. If we'll make it bigger, then we'll able to see it. I have made two lines at 0.02 and 0.04, and at this two line I have compared the mean u velocity component in x direction. So it is very simple to compare the velocity profiles like this at different location, and once we have calculated the different properties, we can compare the different properties at a different location by this making lines wherever we want. Like if I want to compare one more how the velocity is changing at 0.06, I will again come to the slice, and from this data I will plot over line. Okay, so in the plot over line, now I have to I have to make this line at 0.06. so I am doing the same here, 0.06. okay, so this is my third line, and I want to plot the other values. So here when I have plotted, there are so many values they are showing presently. I need just the mean velocity component in x direction. Okay, how it is changing in y direction. So you can see this is my another velocity profile. Okay, and this name I will give x x is equal to 0.06 at this location. So I have made three lines at different location. The lines we can see here. Okay, all the lines we can see here. There are three lines, 1, 2 and 3, and over this how the velocity is changing. So it is very simple to make one dimensional plot, and we can compare at different location. A comparison of different parameter can be made here. Here further the requirement, we need to put the values, what is the values on y-axis, what is the values on x-axis, so that also possible. And from here, like I'll go down and I will try to write what the values in x-axis it is representing. It is actually representing the velocity component ux. So that I will try to write. Okay, so we have to see the label. Here I am searching for the label. So here bottom axis title, here I will write it is actually u, right? So when I will write u, you will able to see u is written here, but it is actually a ux. It is a component of velocity in x direction. So I want to write u underscore x. Like if I am writing like this, it will come like this, but I want to write underscore. So for that I am going to put the dollar sign here, and I will use my latex command, and from the latex command, if I'll do that, it will make u subscript x as it is shown here. So in the same way we can write very complicated expressions at using this ParaView. In the same way, like I want to write what is the values for this vertical axis. So that is actually y. It is the distance in y direction. So I will go and I will find out where I can write give the name for vertical axis. Left axis title, this is actually left axis title, so I am going to give y. So it is fine, it is coming y. Okay. Now I will show you a complicated differential complicated expression how I can write in this axis. Just for example, if I want to write du by dx and some expression, so I will use the latex code. Okay, so my plan is what I want to write just a complicated expression in place of ux. So if I am knowing latex command of that expression, I will just put here. I have already written, so I am just putting here. So I am writing fraction partial u partial x like this. So let us see how it is coming. You can see dou u by dou x like this. So any expression can be written easily using ParaView. It is a excellent post-processing software. Now we will come to the three-dimensional plot, and as we are having the values of q function is what? It is able to present the vertical structure involved in the flow field, and it is used to present the vertical structure for instantaneous flow. Okay, not in the mean data, not in the average data, in the instantaneous data. So we are already having the instantaneous data, and we are now planning to present the q function, the plots of q function. So I am deleting all the plots and coming back to the main data. This is our main data which we are having. So as we are having q function here, you can see the q function we have calculated. Here it is, q function average and q function instantaneous. So this q function we have calculated through our script which we have written in OpenFOAM code, and after computing it, we got this result, and that we want to show here. Here we have to make the isosurfaces. So isosurfaces we can make from this contour values, right? And we'll come here, we'll just see for which isosurface it is making, which parameter is this taking. So it is taking the pressure. I need what? I need the instantaneous value of q function. So now I have applied, and you can see the vertical structure which we are getting. Okay, the vertical structure, actually the negative values and the positive values of q function provide the shearing and swirling region. Here we are showing just one value, that is a positive value. So if we are just plotting all the positive values, we will able to see the swirling structure in the flow field. And if we are plotting the negative values, just for example I am plotting the negative values, so I am plotting the negative value, that is minus 1000. Okay, and when I will do apply, it will show you the shearing region. Okay, it is taking time, it is showing the shearing region. But here I have plotted a very low value, that's why all over shear is present, that's why it is showing like this. If I use little larger value like 5000, the plot will look a good plot, we'll able to see. Okay, I have to increase some more. Okay, so this is the shearing region. Actually we need to plot in a range so that a qualitative, a good visualization of the flow will be shown. We have used different range of q values, and we plotted this shearing and swirling structure as it is shown here. Just I am showing this is positive values of lambda, and q function is here. This is negative values of q function, and this is the positive values of q function. This is the positive values of q function. It is showing the swirling region. Okay, this is the negative values of q function, showing the shearing region close to the plate, how the flow is coming, and this is all shearing region. This is swirling region. Okay, again shearing region, swirling region. This is for the vertical impingement condition. So like this we have plotted many more plots through ParaView, and I want to show you some more plots which we have plotted through ParaView. This is the comparison of Taylor scale. This also we have plotted using ParaView. It is a very nice plot. And then this is from ParaView only. At different location we have compared the values of u bar divided by u max and y divided by y 0.5. It is actually self similarity analysis. So that also we have plotted here. There is another plotting software. If you are very comfortable in TechPlot also. So the TechPlot can load the OpenFOAM data directly, as I am showing here. So here you can see the different kind of data can be loaded in the TechPlot. Here we are having the OpenFOAM control dict. We have to load the control dict from our data. It will automatically take the 0.4 and 0, these two data. It will be loaded in the TechPlot. So I am calling the control dict file. The control dict file is inside the system, so I am calling like this. The TechPlot has loaded the data, and here we can see the data. Now we'll come to the recent data, that is at 0.4. Okay. So we can see the computational domain is loaded, but we have to see from the front, which is this side, right? And we can plot the different contours. We have to take slice and we need to plot it. So first I am planning to take slice at the mid plane. Okay, so for that I am taking a slice, and details are here. The slice is actually x plane. That means it is perpendicular to the x-axis. I need perpendicular to the z-axis. Okay, so now you can see the slice is going from this location, blue dots. Okay, when I will extract the slice, it is going to extract it. Okay, like this. So it has extracted the data into the slice, which we can plot by plotting the slice data. As we are planning to show the slice data, we have to hide the other zones, which is here. So I am just removing all the other zones, and slice data is only there now. So here now if we want to see the contours of any variable, just we have to click the contours, and you can see this is the instantaneous values of k is represented. If I'll go to the variable name, that is k, we can plot whatever is available. Like here, if I want to plot the mean values of velocity, so I will go here, u mean component. Okay, this is mean component of x velocity, mean component of y velocity. Okay, like this, the components of mean velocity is presented here. U prime, if we want to plot u prime, this is the u prime mean, which is a fluctuating part, component of Reynolds stress. Similarly, we are having u prime, v prime, like this. There are different variables which we can plot and analyze. Herewith I am going to stop the discussion as the video is going too long. Here in TechPlot also, one-dimensional, two-dimensional and three-dimensional plot can be made easily, and sometimes it is helpful, and there are some benefits over the ParaView, and ParaView is also having some different quality, so that the difference and the benefits, drawbacks can be further discussed in some other sessions. For time being, I am going to stop this as it has taken a long time, and it will take a long time to discuss all and each different aspects of TechPlot and ParaView. I would like to thank you very much.